Okay, so just one little mistake in the notes last time. When we defined this Darcy flux, I accidentally put the volume fractions in there. They shouldn't be there because by definition, this is the velocity of the fluid with respect to the solid, right? So it's not some partial velocity, so it's not the total velocity and we're taking the partial volume to get the partial velocity. It is the velocity of the fluid with respect to the solid by definition, okay? So today we're just going to quickly cover the linearization of specifically this equation because we already know what the linearization of the conservation of momentum equation is. But we'll cover what the linearization of this is, and ultimately these will be the equations that we solve when we code this up later in the semester. All right, so the term that we want to look at really is this, or the expression we want to look at is this guy. All right, well, the first thing we're going to do is if we just look at what d alpha dt is, well, if we make the assumption that, so we're looking to linearize this, so we're talking about small deformations, small elastic deformations. And so for small elastic deformations, remember alpha is just 1 minus k over ks, right? Well, so these are essentially material constants, especially in the case of linear elasticity. The bulk modulus doesn't change over some small displacement. So this thing is not going to change with time, okay? So then therefore, this whole term goes away, right? So then the next term, let's look at this term. Well, let's look at what the material time derivative. So let's look at what the material time derivative of J is. So I'm gonna come over here. So of course J is rho 0, the initial density over the density, right? So if I multiply both sides through by the density, and of course this is the density of the fluid, but for these manipulations I'm just going to leave the subscripts off, right? So we have this thing. So then let's take the material time derivative of both sides. This is similar to a homework problem that you had, but in the homework problem I think I just said the regular time derivative, ddt. Okay, so of course on the right-hand side that's going to be 0, right? That's a reference density, so it doesn't change. Okay, so then we have d rho dt j plus d rho dj dt. That's equal to 0. Right? Well, what's d rho dt equal? We can use conservation of mass, right? Conservation of mass is d rho dt plus rho V equals to 0, right? So if we plug that back in up there, then we get J minus rho this is divergence of V. Divergence of V, okay. Yeah, plus dj rho j dt equals to 0. So plugging that back, plugging this in right there. Okay, well the rho's cancel. Yeah.
Would it be small d or capital? Or d
In this form, it's capital D. If you remember, conservation mass is either d rho dt plus this guy equal to 0, or d rho dt rho. If you go back and look, these are both equivalent statements. So anyway, back to this term. All right. So then we have dj dt, which is what we're looking for, is equal to j times the divergence of v. All right. Well, let's write out what the divergence of v is. So we have j times partial v1 partial x1 plus partial v2 partial x2 plus partial v3 partial x3. Right? Well, does anybody recognize what that is? It's the trace of the rate of deformation tensor, DII. Right? And if you remember, when we talk about small strains, we said that DII is equivalent, roughly equivalent to the trace of the small strain tensor, right? And you had in your first homework, one of the plots was showing that, right? Had you compare the small strain tensor and the rate of deformation tensor for different displacements, right? Okay, so then ultimately we can write this as J E dot I. So dj dt is equal to j. So let's plug that back in, right? This expression becomes alpha over j EII times j. The j's cancel, and then we just have this term. All right? So when we write it out, now remember in the case of small strains, there's no difference in the reference and deformed configurations and the material time derivatives just become regular time derivatives because the convective terms are small, right? And so, and likewise for this term on the right-hand side, again, there's no reason to do this push forward, pull back operation in the terms of small strain. So we just have that this term over here on the right is just this, where this is just the relative, or if we use the Darcy flux, then we had this guy, right? And for the purpose of what we're going to do in this class, we're even going to just ignore gravity. So the only problems we'll solve will be two-dimensional in the plane that gravity is acting normal to. So we'll ignore gravity. And so then we just have this guy. So I should say ignoring gravity. So then finally, put it all together. I'm even going to, well, okay, I'll leave it. All right. So that's the linearized form of the conservation of mass. And of course, the linearized form of the momentum equation is just what we have always had. And we're going to solve the equilibrium equation, right? So we won't have any inertial terms. So these two equations are the linear poroelasticity we're going to solve. So what are the unknowns in those equations? Pressure, clearly, right? Yeah, and stress is a function of strain, which is a function of displacements, right? So you have also displacements here, right? So you have, if I plugged it all in terms of displacements, you'd have this equation. Remember, this is a stress that it's the effective stress minus the pore pressure, right? So so you'd have displacements in pressure in this equation and displacement in pressure in this equation. Right? And in this case, the only time dependence is in the diffusion. So we're gonna ignore inertia in the solid, which is typical certainly in a petroleum engineering geomechanics setting. If you're doing earthquake engineering or faults or landslide type stuff, then you certainly want to include inertia. Right? But so these are the equations we're going to solve. And you can see if there's no displacements, right? If there's no displacements, then the equations decouple and you just get the diffusivity equation that you learned in reservoir geomechanics. I mean, in reservoir simulation. So it'll be a little while before we see him again because we've got to learn some basic finite element stuff. But at the end of the class, your final project is going to be the finite element solution of these equations. Okay.